Yeah, so we recently changed the mining proof of work algorithm, and that was to disable all of the existing ASICs that we recently discovered were actually mining on the Monero network. Okay, if you look at the hash rate charts from about December last year, there's a big spike, or November into December, yeah, and let's see, the hard fork was March, April, yeah. And we saw after the April hard fork, the hash rate dropped more than half. It kind of recovered to about half of where it was before. So we know for certain now that the original proof of work algorithm, which was supposed to be ASIC resistant, has been beaten. It's been defeated by the ASIC builders, and the new one that we deployed in April was just basically the same algorithm with a couple of things tweaked, a couple new instructions added, not much else to it. So it had very little impact on the hash rate that you would have observed. If whatever your mining rig was doing before, it's only a couple percent different. And that was only a stopgap, a temporary measure, because we just had to get something out quickly. Going forward, people have said, oh, Monero is so stupid, they're going to keep changing the hash algorithm every 6 months. It's like, no, that would be insane. You can't get miners to deploy that. You can't get exchanges. So we are looking for something that's more permanent, more long term. Now, in the upcoming September fork, there's going to be another set of minor changes, minor tweaks. All right, and again, that's just going to get us another 3 or 4 months down the road. We've benchmarked that already, and we know that it'll have minimal impact on CPUs. It'll have a noticeable impact on GPUs, but it will make all the ASICs and FPGAs at least 16 times slower. So we've already seen that. But again, once that gets out there in the wild, within about 3 months, the ASIC guys will be able to adapt to it. That's about the time we've seen from April till now. People are now saying, oh, there's a new ASIC out that can do the new kryptonite version. So that's kind of time frame we're dealing with. So going forward for the long term, we're looking for things that we can deploy in there, and they'll be good for a few years. Just like the original kryptonite got us from 2013 till today, basically. So what I proposed, first of all, is to look at, what makes an ASIC fast, and why are they a threat? How do they do what they do so much better than CPUs or GPUs, right? And the answer is pretty simple. If you look at how hardware is built, ASICs are actually not clock for clock. They're not as fast as CPUs, all right? They tend to run on 2 generations older silicon, all right? So they don't have the same clock rates. Today we've got AMD and Intel CPUs with, base clock rates around 3 or 4 gigahertz. And the ASICs you see being deployed out there have clock speeds around 600, 800 megahertz, right? They really aren't that fast, okay? What makes them effective is that you give them a nice canned little algorithm that's very small, very compact, takes very few transistors to implement, and they can just do that without any of the overhead that a CPU has, okay? And so that's their main advantage. Their advantage is simplicity. And the problem that I see with all the proof of work algorithms we've used so far is all of them were designed to be simple. If you look at the Bitcoin algorithm, it's SHA-256, right? SHA-256, runs in literally, 128 bytes of RAM. It needs next to nothing, okay? And it was designed to be that way. It was designed to be simple. It was designed to be compact because you wanted to use SHA-256 to validate signatures on, multiple megabytes of data as they're going through your networks. So it's designed to be small and fast, all right? And so you can see now that, Bitcoin mining, you look at their network, it's what, petahashes per second? It's this insanely high number of hashes per second because the algorithm itself is so simple. right? And the ASICs that they can deploy at it, they can build a single chip with thousands of compute units on it. So every compute unit can do a hash, several hundred hashes per second. You put that on a chip with 1,000 units, and you're doing 100,000 hashes per second just on a single chip, or whatever the numbers are now. They're kind of insane. For Kryptonite, the idea was, okay, we're going to make this memory hard, right? We're going to use a scratch pad that requires 2 megabytes of RAM. Now, in 2014, 2 megabytes of RAM was very expensive to put on a chip, all right? But hardware technology is doubling all the time, all right? RAM density doubles every 3 years. Okay, so from 2014 to today, memory prices have gone down like this, and so it became practical within the past 8 months to put large amounts of RAM on an ASIC and say, oh, we broke in Kryptonite. So that was one of the things that you have to look at. You can't use a simple algorithm, because ASICs are great for that. You can't rely on memory being an obstacle, because memory prices keep dropping and memory capacities keep rising. So what you really want is something that CPUs can do very well and that ASICs can't do very well. And so what are those things that they can do? CPUs are designed to be general purpose. They're designed to run equally well on any kind of algorithm you can throw at them. And on very large and very complex ones, right? So they tend to be built with, very large caches. You look at an Intel CPU now, it's got like 32 megabytes of level 3 cache. So you can't be playing with little data sizes like 2 megabytes. That's not going to do it. And you want something that can't be defined in a small number of steps, like SHA-256. Right. So the proof of work that I've proposed is randomly generated code. All right. So because the code is randomly generated, nobody can sit there and analyze a single set of steps and put them in silicon. All right. The other thing about it is, okay, so the random numbers that you're feeding into this thing have to come from somewhere, right? And so in this proposal, they still come from the previous hash of the previous block, right? So you're feeding the same input to this thing as you would into the old Kryptonite algorithm. That hasn't changed. But what you're doing with it is you're using that hash to initialize a random number generator. And the random number generator we're using, it's not cryptographically secure, but we don't actually need that. All we need is for it to have a very large number space. Okay, in this case, we're using something that's got a period of like 2 to the 230th. Okay, so it'll take 6 deaths of the universe before that ever repeats. All right, and so we're looking at a problem space that is so vast that nobody could ever encode every possible state into a single chip. Right. So that's the other thing we're doing. And okay, so we have this really great random number generator. We're never going to repeat a sequence in anybody's lifetime. And then with these sequences, now we're generating code that a general purpose computer can execute, but that an ASIC would have trouble with because it doesn't know what's coming next. So really, if you're an ASIC developer and you want to attack this problem, what you're going to have to do is build pieces of a CPU into your chip. You're going to have to build an instruction fetcher, an instruction decoder, and a branch processor, because this code is going to be very branchy. It's not going to have any straight line processing in it at all. All right. And then you say, okay, that's great. Now you're generating a random program. Well, what kind of program are you going to generate? Because if you just generate machine code, that means you give an advantage to, say, x86, and you put any other kind of chip at a disadvantage, such as ARM64, which is getting very popular these days. So say, okay, we're not going to generate machine code because that would be too discriminatory. We're going to generate JavaScript. Now, JavaScript is a horrible programming language. I hate it. It's disgusting. It's terrible. But all the things that make it terrible and make it really difficult make it perfect for proof of work, because it is such a difficult language to process. All right, it's a very slow language. If you write any code in JavaScript, you're 1,000 times slower than machine language or whatever. All right, so it's a great choice because even processing a few instructions in JavaScript requires a lot of branching inside the machine. All right. Now, the other thing about this is when you choose a language that's not machine language, there's the possibility that someone will have a better interpreter for it than you do. All right, someone will optimize the hell out of it better than you. But for a language like JavaScript that's been around for decades, and the big browser companies have been beating their heads against the wall to optimize it for the past 5 or 10 years, the likelihood that they'll succeed at another breakthrough optimization is pretty low, right? So it's a pretty safe choice because you can be fairly sure that how it performs today will be the same way it performs 5 or 10 years from now, right? And so that's what we're looking for. We're looking for an algorithm that we can put in there for the long term so we don't have to keep changing it every 6 months. You know, this one will change itself every time because it's using a random number every time. And I think that's the essence of, yeah.
So in other words, explain algorithm 12, is the solution checking for the output of the code or the structure of the code, or what exactly is?
Yeah, there's multiple steps in here, right? First of all, we require that you actually generate the source code for a program, randomly generate, and so that source code gets fed into the hash. All right, so partly, we require you to generate the correct source, right? And then the program has to run, and the program will always produce output at the end.
Is there like a halting issue at all in there? Or?
No, because the generator has been fixed, so it won't generate infinite loops, all right? And, stuff like that. Yeah, there's no problem there. So then the program has to run, and then the output from the program is collected, and that's hashed as well. All right. Now, between the step of generating and producing the output, you could try to cheat. You could say, I'm going to generate this JavaScript code, but at the same time I'm generating this, I'm going to generate matching machine code for it. Okay? And I'm going to skip the interpretation phase, and I'm just going to run the machine code. Now, there's an interesting thing, though. In JavaScript, because it's an interpreted language, it actually has a function that says, evaluate this arbitrary string of text, as if it was JavaScript. All right. So we can also generate these statements in the output. So basically, that forces you to have a JavaScript interpreter in the middle of this process. All right. Okay. So then we take a hash of the output, and then since all of that comes from the same input, we know that you started with valid input, you generated valid source code, and you ran it correctly. Right.
And for those who don't know the name of this wonderful.
Well, there's actually 3 things going on now. Well, only 2 now. So the current one for Monero is called random.js, just random JavaScript. There's another group out there with one they call ProgPow, so programmable POW, programmable proof of work. And I actually advise them on that design as well. I'm not as fond of it because that's targeted directly for GPUs, and that's great for them, but it will run poorly on CPUs, right? And in the random.js case, we're a little bit opposite. It'll run really well on CPUs. Today, it won't run very well on GPUs, but there's nothing architecturally against that. It's just that nobody has a JavaScript interpreter that runs on GPUs yet. Right.
It's weird to think about.
Yeah.
So how much consensus is your idea so far?
Well, at the moment, it's still a highly experimental idea. It needs to be tested pretty heavily. Nobody has any strong support for any competing ideas at the moment. So
here's the issue if you don't go the other way and just continue to change the algorithm. A, you have to keep it secret from the ASIC makers. Now you've invoked secret centralization where you have Cabal keeping secret numbers, and if they get out, you built in the possibility of corruption.
Yeah.
And then that can be socially attacked a number of ways. You just don't want that kind of.
Yeah.
That's not anti-fragile, and that's against everything that Monero and I was practicing.
Exactly. You don't want that responsibility. You don't want that target. Yeah.
It's a necessary evil for now, but if this were not possible, if this were the end of math, and there were no other ways, like, honestly, the most ethical thing to do would be to be reduced to SHA-3 or SHA-256, because then at least it's equal playing field. It's got to be equitable above all other things right now.
Sure.
It's hard to
Yeah. No, it's a valid point. I mean, at the end of the day, we want it to be, egalitarian. Everybody has to have an equal shot.
Yeah. So you mentioned the evaluator.
Yep.
So for every hard fork, just with that portion, just run the evaluation of whatever change, or sorry if I
for every hard fork.
Or when would it? Maybe I don't understand. For every hard fork.
Well, okay. With random.js, I'm hoping we won't have to tune it again for a long time.
Okay.
Because it's just going to be random every time.
Just every time. Okay.
Yeah. Yeah.
Okay.
Yeah.
So is that hard fork? Is that just changing the code, or is that separation and deviation into two separate viewpoints?
Oh, no. Yeah, we're not going to separate into multiple coins.
This is the Bitcoin Cash situation.
Yeah, right. Yeah, so, but, this is not going to get deployed this year. It's not ready for September, right? So at the earliest, we'll probably roll it out next April.
But you do have two upgrades every year.
Yeah.
That's the point you're asking.
Non-contentious.
Yeah.
The big deal about Bitcoin is they don't have any hard exposure to the social code, so it's always thinking about what we're going to fork on. And now the special interests want to coin so they can plug their own coin if they get their biggest thing.
Yeah.
If you see a fork in Monero that doesn't upgrade to the new numbers, that's probably going to be the ASIC makers that want to stand their ASIC flat number.
Yeah, just like they did on the last fork. Yeah.
So that's what happened.
Yeah.
Okay.
How does potential Lightning Network play into any of this, or is there any? Does Monero benefit from?
We've talked about Lightning Network being adapted for Monero at some point. There probably is some benefit, just as a layer 2 scaling solution. Sure, it's not a real high priority at the moment. There's other holes to patch.
Is all this going to play nice with Tari and whatever? When Tari comes out?
Is what?
All these things going to play nice with Tari?
Yeah, the story is that, Tari is running all their stuff merge mined with Monero, so they're going to stay compatible.
I know you're not primary in Tari.
Yeah. Yeah.
How big is it?
That's about that.
Yeah.
All right.
All right.